Oh, good afternoon. Today we're going to be looking, this is a long assignment, systems of equations, matrices, determinants and Cramer's rule, which probably means nothing to them. So what we're going to be looking at today are finding points of intersection. If you have two lines drawn, there's two ways or three things that could happen if you were just going to draw two lines. More than likely, they would intersect in 2 points. In one point, okay? Two lines most likely intersect in 1 point. Would it be possible for to draw two lines and they intersect in exactly 2 points? Say no. No, we're going to draw two lines and they intersect in 2 points. But you could draw two lines and they never intersect. What do you call lines that never intersect? It starts with a P. Parallel. Okay, So parallel lines will never intersect. And then there's one other case that you might not even consider it a case. If I drew two lines, if I drew a red line and a blue line, on the blue line right on top of the red line, then how many points is it intersecting? Infinitely many points. Yeah. One line on top of another line, those are called coincidental lines, and there are infinitely many points of intersection. Let me write all of that down. Infinitely many points of intersection. They're intersecting in every point, right? Right. That's not very interesting. Parallel lines, they never intersect. But the most common situation is this one here, two lines intersecting in exactly 1 point. And so today we're going to look at methods for finding that point of intersection. And recall, you shouldn't be expecting any exponents. We're looking at lines, and lines have no exponents. So we're going to see a couple of methods for finding these points of intersection. The first method is something called substitution. And I'm going to go ahead and go to the first problem and write it down. By the way, even though this stuff is sort of lengthy, it's not really hard. Okay? This assignment is sort of lengthy. It's not really hard, because this assignment has a whole lot of small topics all blended together into one assignment. I didn't want like 4 assignments with 3 problems each. Okay? Actually, it would have been 6 assignments with 3 problems each. Instead, we made 1 assignment with 18 problems. Okay, so question 1, it says, solve the following system of equations. That's what you call 2 or more equations. Like here, the equation 9x plus 2y equals negative 21. There's no exponents. It's a line. X equals 6 minus 3y. No exponents. It's a line. So we have 2 lines, and we're going to find the point of intersection. Let me write these down. Solving the system means find the point of intersection, or points. X equals 6 minus 3. Okay, so you're solving this system of equations using substitution. What we're going to do is rewrite these 2 equations in such a way that we just have 1 equation. Right here we have 2 equations and 2 different variables, x and y. With the substitution method, you substitute 1 variable in for the other. Like right here, this is x equals 6 minus 3y. If you're going to use substitution, one of the equations has to be in the form variable equals something else. And if it isn't, you have to rewrite it. If that 3y had been over on the left, to use substitution, you would have had to move that 3y over to the right.
And
but
that'll
you
be
need
the
one
next
variable
problem.
isolated to use substitution.
So this is x equals. So what if we took this 6 minus 3y and plugged it in for x? That's going to give us an equation that we can solve. In place of that black x, I'm putting 6 minus 3y. We're rewriting two equations with two variables as just one equation with just one variable. Notice we now no longer have any x's, just y. And this is a linear equation. So how do we solve a linear equation? Well, I'll distribute the 9. So we have 54 minus 27y plus 2y equals negative 21. I think I would combine the y's, negative 27 plus 2. I'm going to write that as 54. And then negative 27 plus 2, is that a negative 25y? See, at this point, it's a linear equation, so you're just trying to isolate the variable. So I combine the y's together. Now, if I'm trying to get this y by itself, the next thing I would do is move the 54. So in other words, I'm doing what? Am I subtracting 54? So I have a negative 25y on the left. And what am I getting on the right? Negative 21 minus 54. That would be negative 21 plus negative 54. Is that a negative 75? Okay. Only one thing left to do to solve for y. And what is it? Divide both sides by negative 25. Good. Negative 75 divided by negative 5.
Negative 20.
Divided by negative 25 is what? Y equals 3. Okay. Now, we're looking at a point of intersection. A point of intersection is an ordered pair, x, y. What we've just done is found the y coordinate of our answer. The y coordinate is 3. Y'all have any idea of what we could do to find the x value? If we know that y is 3, what's the name of this method?
Substitution.
If you know one of the variables, then substitute in to get the other one. Like right here, if I want to figure out x, if I put a y right here in place of this 3, I would have...
In place of that.
Excuse me, in place of the...
in place of the y.
Yeah, if I put a 3 in place of the y, sorry about that, I'd have x equals 6 minus... Well, let me go ahead and write the one I'm plugging into. 3 times 3 would be a 9. So what are we getting for x? 6 minus 9, negative 3. So there's our point of intersection. Negative 3, comma 3.
Now, if you were to have taken that y value of 3 and plugged it into the first equation and solved for x, you would have still gotten negative 3. But if you have one equation already solved for a single variable, that's the one, that's the easier one to plug into. So we come over here to number 1. Well, let me type this answer in first. Negative 3, comma 3.
Going back. You know, there's a way you can check your answer without actually plugging it in. If this were a test and you were wondering, is this answer right? You know, when you're taking the tests and quizzes, it's like a real test where it doesn't tell you what's right and wrong until the end. Okay?
Well, it is a real test. What do you mean?
I mean
like
a paper test.
Oh, a paper test.
Okay. If you take this for X and this for Y, if you plug it in up here, you better get negative 21. 9 times negative 3 is negative 27. 2 times 3 is 6. Negative 27 plus 6, is that giving me negative 21? Yes. And then doing it down here, we know it's going to work out, because that's what we just did. If we plug a negative 3 in here, and a positive 3 here, 6 minus 9 is negative 3. So this answer better make both of these equations true.
Realize with substitution you need one equation solved for a single variable. Suppose you want to use substitution and the equation's not already solved for the variable, then you're going to have to solve it. To illustrate, number 2, does that do it?
Okay. Number 2, there's an extra step in this one. Let me write down these. We have 4x plus y equals 18. And 7x
minus 2y equals 9.
Okay.
Switching over.
Okay. Well, we're told to solve this with substitution, and what we're about to do is just the most classic problem-solving technique. Make this problem look like number 1. In number 1, there was this second equation here. It said variable equals. So we plug that into the other equation. Well, here we don't have the x or y equals. So you've got to do that yourself. You look at the two equations and ask yourself, which one of these variables can I isolate the easiest? By that I mean not getting a fraction. If you wind up having to get a fraction, substitution's not the way to go. Which one of these variables would be the easiest one to isolate? The black x, the black y, the purple x, or the purple y? The black y. All I'd have to do to get that y by itself is move that 4x over. Now, it's like problem 1. You take the 18 minus 4x and plug it in for y. I should have, instead of saying plug it in for y, what word should I have used? I should have said substitute it into y. So we have 7x minus 2 in place of the y. I'll put 18 minus 4x and go about, get rid of the parentheses, combine the x's, and isolate the x. So we have 7x. Is that going to be a minus 36?
Yes.
And a plus 8x?
Yep.
So I get rid of the parentheses, combine the like terms. I can combine the 7x and 8x. So that's 15x minus 36 equals 9. Oh, wow. We're going to wind up with 3 again as an answer.
Yes, it is 3.
Well, so if in doubt, guess 3, and I'm joking about that. That's just the luck of the numbers here.
Look at the draw.
Yeah. 9 plus 36 would give a 45 over here.
Divide both sides by 15.
Mm-hmm.
And it turns x equals 3.
Yeah,
So that means these lines are intersecting at an ordered pair where the x-coordinate is 3.
so here's what our answer is going to look like. It's going to be x, y. Uh-oh. Well, how do we find the y value? Well, it's called substitution. Substitute. Take this purple 3 and plug it in for any x you want up here.
What's the easiest equation to plug into? You're trying to find y. The top one where it's already solved for y.
Yeah, if you take this, y equals 18 minus 4x. If you plug the 3 in right here, you'd y equals 18 minus 4x. Replace the x with 3. So we have y equals 18 minus 12. We're going to wind up with y equals what? 6.
So these two lines intersect at an ordered pair. If you drew their graphs, they'd intersect at the point 3, 6.
Mm-hmm. Now, I want to go back for a moment and mention something. We said that there's two cases that aren't very interesting. There's two cases that aren't very interesting.
See, I think those are the interesting cases. They don't occur that often.
The parallel and the infinitely many. Here's how you can tell when that happens. When you're going through all this work here, if every variable subtracts out and you wind up with, for infinitely many, if everything subtracts out and you wind up with a number equal to itself, if you're working through this and all of a sudden every variable subtracts out and you wind up with something like 3 equals 3, that means it's infinitely many. If, on the other hand, you wind up with everything subtracting out and you get number equals a different number, something like 3 equals 5, that's when you're going to have the parallel no solution. Okay? But that's not going to happen. We're doing what I call the more interesting cases where we have the solution.
So
my brother says, it was 3, 6. Okay,
but if you were going through and you were using substitution or the new method, elimination, that we'll see in a moment, and you wound up with 3 equals 3 or 7 equals 7, no variables left. When you substituted every variable subtracted out, you'd choose B. But if you went through using substitution or elimination and all the variables subtracted out and you wound up with something like 3 equals 2, no solution.
And that's just a little extra because it's not going to actually be what happens.
You want me to take over with the elimination for a while?
Okay. So those first two problems, we did something called substitution. Now we're going to do something called elimination.
Tony, aren't you glad that I convinced you that it was right to sit down and do this rather than standing all the time? As I stoop to new depths of laziness, I've convinced my brother we should be sitting down doing this. It's easier to write. I'll tell you that much. When you're writing on a tablet like this, it's easier if you're sitting down. So we want to solve by the elimination method. The only way to discuss the elimination method is to look at an example. And this is an excellent example. Okay? So we have x plus 6y equals 59, and negative x plus 4y equals 31. And let's switch over to my tablet. And here they want us to use elimination. The idea behind the elimination method is to have, first of all, make sure you have your like variables aligned. And you need to have the same coefficient on one pair of like variables, but with opposite sign. When I look here at x, the coefficient on this x here is a positive 1. I don't see a number there. So that number in front of x is a positive 1. What's the coefficient on this term here? A negative 1. They have the same sign, they have the same coefficient, but opposite sign. If we were to add these two equations together, if these two quantities are equal, their sums should be equal. So we should be able to add the left side and the right side and get a true statement, or an equivalent statement, I should say. X plus negative x, what's just happened there? It was eliminated. That's the name of this method. Adding them, they subtracted out. Well, you have a positive 6y plus 4y. That gives us a positive 10y.
Then it will turn into 90.
And 59 plus 31, I agree, is 90.
Divide both sides by 10, so you get y equals 9.
Okay. I remember we were teaching at Baylor, right once we got our master's degree. The textbook was written by one of the faculty members there, and when they were using elimination on a problem, they used strict elimination. Well, that seems a little, I found that a little bizarre. What's normally done is that you use elimination with a combination of substitution. Rather than saying with strict elimination, we'd say, 6 and 4. They need to be the same number with opposite signs and do it all over again to eliminate y. But we don't need to do that. We know once you have one variable, we know these lines are going to intersect with a y value of 9. We can find the other variable by using the substitution method. Well, which equation do you want to use? You're going to have to substitute 9 in for y into one of these. Well, which equation do you like better? It's really up to you. The top one or the bottom one?
I think most people would dislike that negative x.
I think so too. I think that most people would use this first one because the x doesn't have that negative in front of it. So let's do that. We're going to say we're using the equation x plus 6y equals 59. We're going to substitute 9 in for y. So we have x plus 6 times 9 is equal to 59. 6 times 9, that's 54. So we really have x plus 54 equals 59. There's only one thing left to do to find y. To find x. What is it? Subtract 54 to give us x equals 59 minus 54 gives us an x value of 5. So these two lines intersect at the ordered pair 5, 9. To use elimination, you need the same coefficient on a pair of like variables, but with opposite signs.
Let's check it without punching it into the to my math lab. Plug the 5, 9 in here.
Okay, 5 plus 6 times 9, that's 54. 5 plus 54, sure enough, that gives us 59. Suppose we plug the 5, 9 here. That'd be a negative 5 plus 4 times 9 is 36. So negative 5 plus 36. Does that give us 31? Yes, it does. But of course, we're going to check our answers just by typing it into my math lab. But on a test, it's not going to tell you, as soon as you type in the answer, that's wrong. So that's the way you check this.
Look what I'm about to do. I've typed in 5, 9. I check it and it says wrong.
What did he not do?
What did I not do?
Parentheses.
That's right. And that's one of those things when you're taking the test. You've got to be careful. That's why you're given two opportunities. If you make a mistake like that or mistakes like that on the first go through, you can do it again and hopefully remember to put the parentheses. Any questions there? This one was tailor-made for elimination because it already had the like variables aligned and it already had the coefficient, same coefficient but opposite sign. Well, let's look at the next one. Oh, well, this one does. I think this one is pretty nice, too. I wasn't expecting that. Okay. Okay. Solved by the elimination method. Oh, switch back to this one other time. Realize, by the way, the instructions for number 3 said use elimination, but you could have used substitution. If you had used substitution, you would still get the same ordered pair, 5, 9. I think you could say, oh, I'm going to solve for this x right here. Move that 6y over, substitute it into the other equation. So substitution would have worked, and you would have gotten the same answer. And it wouldn't have been that hard to solve for the variable. But let's look at number 4. I think number 4 is definitely one for elimination is better.
But I generally think elimination works better.
Well, that's the method I prefer, okay? But I'm trying not to prejudice these people. But I prefer elimination. And now they know that. Okay, make sure. 8x plus 8y equals negative 40. Let me make sure I didn't miscopy the problem. And 5x minus 8y equals negative 64. Okay. This was another one that's tailor-made for elimination because it already has the like variables aligned and the same the same coefficient but opposite signs. Which variable will I be eliminating? The y. Notice we have a positive 8 and a negative 8. So I was expecting, I didn't realize that was going to happen here. So this is nicer than I thought. Adding the two equations together, that's a positive 8x plus 5x. That's a 13x. And then an 8y plus a negative 8y. That is
8 minus 8, 0.
Okay. And then negative 40 minus 64, that gives us a negative 104. And we have an equation we can solve for x now. Divide both sides by 13 to give us x equals negative 104 divided by 13. Is that negative 8? Is my mental arithmetic correct? So we know these two lines are going to intersect at an ordered pair where the x-coordinate is negative 8. I'm going to write that down. The x-coordinate is negative 8. Remember I said that I use elimination and substitution, and that's what most people do. When the instructions say use elimination, you eliminate one variable and then substitute for the other. That's quicker. So, which equation do you want to plug in that negative 8 for x? Which one do you like better? Do you have a feeling one... generally the one with smaller numbers or the one with fewer negatives or minuses. Maybe the first one? I think the first one might be a little cleaner. Let's see. But realize as long as your algebra is correct, you'll still get the correct answer regardless which one you plug into. So we're plugging in negative 8 for x. So we have 8 times negative 8 plus 8y equals a negative 40. That's an 8. It's hard to tell that that's an 8, isn't it? 8 times negative 8 is a negative 64 plus 8y equals a negative 40. What should I do next to solve for y? What do you think I'll do?
Add 64 on both sides.
Yeah, I'd get rid of that minus 64 by adding 64. That'll give me 8y equals negative 40 plus 64 gives me a positive 24.
Divide by 8 on both sides, so you get y equals 3.
So these two lines intersect at the ordered pair, negative 8, comma 3. Any questions there?
Okay. So this part right here was the elimination part.
Yes. You see this black part right here? That's the elimination part. This part down here is what part? Right here we were using elimination. That's how we found x. And down here, substitution. So substitution and elimination go hand in hand. My preferred method is this combination. Start off eliminating and then substitute to find the other variable. Let's punch in the answer.
Okay. Parentheses, negative 8, comma 3.
And go back to, okay.
Everyone finished with this?
Finish with this one. Okay, number 5. I keep thinking there's going to be a more interesting elimination. Okay. Okay. Number 5. Same instructions. We're using elimination. 8x plus 3y equals negative 11.
So y negative 11? Never mind.
I was like, am I?
Okay.
8x plus 3y equals negative 11. And then the other equation is 3x.
Minus y equals negative 6. I thought you were like, for some reason, adding 8x and 3x, and I was like, why is that negative 11?
No.
Not an x.
No. Okay, let's switch. To use elimination, you need the like variables aligned, and you need the same coefficient but opposite signs. Well, we have like variables aligned, but we don't have the same coefficient. I think the one that would be the easiest to modify would be the second equation on that y right here. Because as it is, what's this coefficient on y?
-1.
A -1. We could change that to a -3 by multiplying through by 3. Remember that when you're that whatever you do to one side of an equation, you got to do to the other. So we can multiply all the way through here, multiply across by 3. Now the first equation isn't changing. It's going to stay at 8x plus 3y equals a -11. But multiplying by 3 on the second one, we're distributing here 3 times 3x 9x, I agree. 3 times a -1y, 3 times -1 is a I agree. And 3 times -2, -6. And now look at what we've done. We have the same coefficient on the y's, but opposite signs. One's positive, one's negative. We can add the two together and eliminate y. Adding these two together, 8x plus 9x, that's 17x. 3y minus 3y. We've eliminated them, haven't we? -11 plus -6 gives me -17. divide by 17, and we get a very nice x value here. These lines are going to intersect when x is equal to -1, -17 divided by +17. So these things are intersecting at an ordered pair where x is -1. We need to substitute to find y. I guess we could plug in the x right here beside the 8 and solve for y there, but it might be easier using the original blue equation. The numbers are smaller, 3, 2.
I don't like that minus in front of the y, though, but that's just me.
Where do y'all want? Let me ask you. I'll let y'all decide. You want me to plug into the black equation or into the blue equation? The blue equation, okay. So we're plugging in. We know that x is equal to -1. We're going to plug into that blue equation 3x minus y equals -2. So we have 3 times -1 minus y equals -2. 3 times -1 is a -3. So we have -3 minus y equals -2.
Add 3 on both sides of the equation.
You know what I'd do? I'd move the y to the right. I wouldn't move the 3. We need to get rid of that negative. I think the quickest way to solve would be to move that -y to the right. What does that become if I do that?
-3 equals
Okay, well,
-2 plus y.
well, so we have here, I'm moving this over. That becomes a positive y. The -y, add it to both sides, it becomes a positive y. Now move the -2. We move the -y to the left. Now we're going to move the -2 over here by doing what?
Adding 2.
So -3 plus 2, what's that going to give us for y? -1.
So the coordinates are -1, -1.
They are, that's right.
To avoid having to move that y around, that's what I said. I thought that I would have gone with the first equation.
Any future teachers in this room, any future teachers, I'll tell you, a classic new math teacher mistake is to work the same problem over and over a different way, okay? And I'm about to make that mistake.
Oh.
Tony thinks we should have plugged into the black equation, so I'm going to show you that we're going to get the same thing, okay? We have time. We're plugging in x equals -1. Let's plug it into the black equation. And I'm thinking, I hate to say this, but I'm thinking Tony's right. I should have just used the black equation to begin
Oh,
with.
you don't have to say that.
Oh, I know that's what you want me to say, Tony. So,
Your
Okay.
insincerity.
no, I'm serious. I think it would have been better. So we're plugging -1 in for x. 8 times -1 is a -8 plus 3y.
Minus -11. We add 8 on both sides to get 3y equals 3.
Okay. Adding 8, -11 plus 8 gives us a -3.
Divide both sides by 3, you get y equals -12.
And sure enough, we got a y value of -1. Any questions there? But any future teachers, math teachers out there, I'll tell you, that's the classic bad
Don't do it.
move. Don't work the same problem different ways, okay? So invariably, it causes confusion. But I agree. I like it like that. I'll remember that for class on Monday. Any questions there? You need the same coefficient with opposite signs. So I'm going to write that out. Elimination. Here's what you need. You need like variables aligned, need like variables aligned.
So the x's should be lined up and the y's are lined up.
Right. And you need the same coefficient but opposite signs on one of the variables. Need same coefficients but with opposite signs on one of the variables. And make a note, you may need to multiply one or both equations by a number to get those same numbers of the same coefficient but opposite signs.
And the reason you say maybe both, theoretically, you could have made both of these numbers 24.
Look at that, 8 and 3. You could have changed them both to be 24. Maybe multiply the top one by 3, multiply through the bottom by a -8. So
then you would have gotten 24 and -24. But you know what? You've done all of that, and I haven't even checked this. Wouldn't it be terrible if you had the wrong answer?
Let's punch in the answer first. I think you've typed in the wrong thing.
Oh, no. Oh, it's -1,
-1.
Okay, I don't put the minus there.
Okay, and now let's go back.
Uh-huh.
You need like variables aligned, and you need the same coefficient but with opposite signs on one of the variables. If you get the same coefficient but opposite signs on both variables, then you're going to have one of those special cases. You'll either wind up with a number equals a number, namely 0 equals a number, or 0 equals itself. Any other questions there? Okay. Next.
Oh, it's now time for you to mention what a matrix is.
Okay. I have a definition, a real vague definition. Definition. A matrix, matrix, is a rectangular arrangement of numbers. Nothing fancy about it. It's just a rectangular arrangement of numbers.
When you have these numbers arranged in a rectangular arrangement, there's going to be rows which are horizontal and columns which are vertical. So why don't you write rows horizontal, columns vertical?
That's a good idea.
Because I'm going to show them how to punch this into the calculator.
Horizontal.
And you're going to need that.
And columns vertical. Let's talk about the size of matrix also while we're talking about rows and columns. Okay. Oh, wait, there. Generally, we enclose a matrix in these little brackets. It looks like the brackets that you use for closed circles in interval notation. Here's an example of a matrix. Let's see, I'm going to 6 and 1/3. Okay. There's an example of a matrix. Notice you enclose the matrix in rectangular brackets that are similar to the brackets that you use for interval notation. The horizontal alignments are called rows. This is row 1, row 2, and row 3. The vertical alignments are called columns. So this is column 1, column 2, column 3, and column 4. The size of a matrix is given in terms of its number of rows and number of columns. Just like this rectangular room we're in here. You don't look at the floor and say, oh, this is a 9 a rectangle here. No, you give it in terms of the dimensions. You give it the number of rows by the number of columns. And I'm using that hashtag there the old-fashioned way. That pound symbol used to represent numbers. So the number of rows by the number of columns. So this matrix I just made up here, we would say that is a 3 by 4 matrix.
And don't multiply them together. Don't multiply 3 times.
Yeah, multiply them, all that's going to do is tell you how many numbers are in the matrix. There's 12 numbers there. Okay?
Yeah, but don't multiply them because you may get confused. You're like, 12 matrix, what does that mean?
Yeah,
It doesn't mean anything. You just you don't multiply them, okay?
But X is just by. Like when you state the dimensions of a room. 20 feet by 30 feet.
In a little bit, we're going to be looking at Cramer's rule. Cramer's rule is something that's applied only to square matrices. Look at the size. Look at the size. The way we determine the size of a matrix. If we're looking at a square matrix,
Isn't it like the width times length times height?
no. What do you think is true about the number of rows and the number of columns? Keep in mind a square is a rectangle with the same length and the same width. So what do you think is true about a square matrix? Same number of rows and same number of columns. The number of rows is equal to the number of columns. And let's look at a homework problem.
Before we do that, the first thing we're doing is something called an augmented matrix.
An augmented matrix is used to summarize the coefficients and constant terms of a linear system of equations.
We don't need to write anything.
An augmented matrix summarizes the coefficients and constants in a linear system.
There's a collection of equations.
A linear system of equations. Those equations that we were solving by elimination and substitution earlier in the class. It's just going to summarize the coefficients and constants. Writing augmented matrices will be one of the easiest things we've done in this class this semester. I'm not sure why I wrote that definition of the... Okay. Let's look at an example of an augmented matrix. Okay, to create an augmented matrix, you need your like variables aligned, you need your constant terms aligned on the other side of the equation. So, notice the first row just contains the coefficients of the first equation. The second row contains the coefficients and constants in the second equation.
This vertical bar is acting as the equal sign. Not much to it. The x coefficients go in what's called the x column. The y coefficients go in the y column. The vertical line acts as the equals, and then the constants over here. Surely the next one will be more involved. Okay. Why don't we call out the numbers that I'm going to be typing in?
Remember, if a variable doesn't appear, we know that if the variable appears and there's no coefficient, the coefficient is an assumed 1. Suppose the variable doesn't appear, then what's the coefficient? 0. So call out the coefficients for x.
I'll move across. Ooh, wait.
You know something? Maybe you should shrink the screen down for right now. Hold on, let me see if I can do it.
Okay,
There.
yeah.
Okay.
So
Call out the coefficients for the first column.
No, first row. I'm
Oh, okay, you're going. Oh, I always go vertical. Okay.
3x minus 1y plus 4z equals negative 9. Then the second equation, 3.
Negative 6, 7, 2. 0.
Okay, that's what you were trying to say, Tim. Where there's no x, you've got to put a 0.
For negative 5, negative 7.
Well, not much to that.
Now we need to be able to go backwards. If you're given a matrix, you need to be able to create the equations associated with that matrix. So look at that first row. That 1 is the coefficient of x. So look at where he's pointing. You have a 1x. What's going to go in that next blank there?
9.
9.
Then 8 because the negative is already
That
there.
negative is already there. That's right.
Then it will be 8.
Okay.
The next one would be 2, and then negative 9, since the 0 and negative 1 are already there. So the next one would be negative 9.
Uh-huh.
So, and that would be 2, 9, and 8.
Okay. Oh, wow. That even...
So notice the zeros, that means the variable doesn't appear in that equation. So I agree, we have a 2x, we have no y, we have a 9z, and on the right side we have a positive 8.
I would sure think it looked better if they lined
Lined
it up, but I
I
guess
know.
that was too much of a programming feat for them to program it so it always lined up.
Any questions there? As I said, this augmented matrix stuff that we're doing, now if you have to take Math 1324 for
Like the business.
then you're going to do a lot with augmented matrices. And you'll remember and you'll think back to this. Well, it seems so easy back in college algebra, but once we get to 1324, Math for Business, we do a lot of stuff called Gauss-Jordan elimination that it is not so easy. We look at matrix reduction. It's an excellent course. Oh, I like this one. They give us the matrix, and they want us to come up with the system of equations associated. Look at that first row.
It would just be 1x. 1x equals 5.
Okay.
Y, then it's just, or just x equals 5, y equals 2, z equals 7.
Any questions there on Jacob's logic? I wonder if you put a 1z, would it count it? Right?
What if you do like, or, oh yeah, it has to be, it does say x, y, z, doesn't it?
Oh,
Yeah,
yeah.
Maybe if we do try 1x, 1y.
I'm just curious. See if just put a 1 there and see if they count it. Okay.
It would be weird if it did, because yeah, it's not the answer they really look for, but it's like still correct.
This is the preferred way of writing an augmented matrix. there's a way to take a matrix like this and do some operations on it and rewrite it so it looks like this.
Now, what's the advantage of having those ones down the diagonal and the zeros everywhere else to the left of that vertical bar? If you could take a matrix and rewrite it so it looks like number 9, don't you have the solution to the system then?
X equals 5.
The number on the right, those numbers on the right are the values of the variables. And that's what we do in Math 1324.
Can you press similar question? I want to see something.
Okay.
Yeah, so it's just going to be...
Yeah, for everyone, you're just going to type in X, Y, and the letter Z.
Okay, I just wanted to see that just to see like if it was one of those questions where it's always going to be the same answer or if it's...
Well, for that it is. It'll change these numbers.
Number 9, that matrix is said to be in reduced row echelon form, and there's elementary row operations that we use in Math 1324 that take a matrix like number 8 and rewrite it like that. Now, I'll tell you right now, it can get messy, but there are plenty of programs online that allow you...
You can do it with the...
Hey,
with
I
this
hadn't
little
even thought of
calculator.
that.
Mm-hmm. But I think I'm going to wait and show them how to do the determinants with the matrix.
Yeah, that'd be better.
Let's not get into something that we don't have to do. Okay? So...
Number 10.
We're now finished with these augmented matrices. Again, this assignment, instead of having 4 or 5 assignments with 3 or 4 problems, we have just one big assignment with 18 problems. Okay? So, number 9.
We've already done.
Oh, yeah.
Determinants.
I'd write up the ABCD.
You would?
Yeah.
Okay. Let me...
The determinant is a way of assigning a numeric value to a square matrix. Notice it's square, only 2 rows and 2 columns.
I'll say it's a unique number assigned to a square matrix. The funny thing is that the properties of determinants, if you take a linear algebra course, the properties of determinants are amazingly similar to the properties of absolute value. You have a triangle inequality, you have almost every absolute value inequality, property that there is can be applied to matrices using determinants. But for our purposes, we just need to know that it's a unique number assigned to square matrices. We're going to find 2 by 2 and 3 by 3 matrices. To denote a determinant, use big vertical bars as if it's an absolute value. Well, because determinants and absolute values have similar properties. I'll say the first row is AB. The second row has the numbers CD. A 2 by 2 determinant is just the difference of their cross products. AD minus B times C. AD minus B times C.
Make sure you do not go BC minus AD. You'll get it wrong every time.
You start even with the 3 by 3 determinant, you always start in the upper left-hand corner. And you'll see what I mean. Multiply minus multiply.
Always start with that first number. Now, and this isn't something, the letters are so important, like the quadratic formula, negative b plus minus. Yeah, the letters are important. What's important here is the pattern. What's called the major diagonal and the minor diagonal. Now, let's look at this.
Okay, this is number 10. They want us to evaluate the determinant. Let me write the problem down. The first row has the numbers 2, negative 5. The second row has negative 8 and positive 3.
So would it be be 6 minus 40.
Okay, let's switch.
Or that would eventually turn into negative 34.
So you multiply 2 times 3 is 6 minus, that minus is from the definition. Then you multiply again, negative 5 times negative 8, that's a positive 40.
But because of the minus, it equals to negative 40. So it's 6 minus 40, which is negative 34.
That's
Negative
correct.
34.
I was sorry.
Oh, that's fine. So, we punch in negative 34. This little thing we're doing here is called crisscross.
Crisscross out.
For finding the determinant.
Okay. Number 10.
Oh, wow.
For a 3 by 3,
Number 11.
pardon me, for a 3 by 3 determinant, there's 2 different accepted processes. The method of using cofactors and rewriting it as a series of sums and differences of 2 by 2 matrices.
And you might see that if you look at view an example or click on the textbook. But that's not how we're going to do it.
We're going to use a another crisscross method for a 3 by 3 determinant that is consistent with what's done in most physics classes. Although nowadays, it's my understanding they just use a TI calculator to find the determinants.
And I'll show you how to do that in a moment. But let's do this first one using the crisscross.
Okay, number 11.
Unfortunately, not as easy as the little 2 by 2. There's a lot more multiplying.
Oh, it's still not bad.
Yeah, it's not hard. It's a little tedious doing it by hand. But it's a little tedious entering it into a TI calculator.
I was thinking the same thing, Tony. Okay. Let me make sure I didn't miscopy anything, because if I miscopied one of these numbers, I'm definitely going to get the wrong answer. There it is. And notice, once again, they're using those big absolute value bars to denote the determinant.
So
my advice to you, recopy the first 2 columns.
Start off by recopying the first 2 columns.
So, that 5, negative 2, 2, I'm writing it. And then 1, 5, 4. Recopy the first 2 columns.
Then you're going to multiply 6 diagonals all together.
And remember, I said you always start, whether it's a 2 by 2 or a 3 by 3, you always start in the upper left-hand corner.
With the first number written.
The first number. Here you go. We have parentheses. 5 times 5 times negative 7. We're multiplying down the diagonal. There are 3 different numbers. That's a 25 times a negative 7. Is that a negative 175?
Yes.
So we have a negative 175. 1 times 1 times 2. The reason you wrote those first 2 columns is so that you see all 3 of the diagonals falling from left to right. You had 5 times negative 7. Now you have 1 times 1 times 2, which is?
Now that we can do without a calculator. It's a positive 2.
Well, I did 5 times negative 7 without a calculator, Tony. So 3 times negative 2 times 4. That's a negative 6 times 4. That's a negative 24. Before we go on, do you see where I got those 3 diagonals?
Multiply, multiply, multiply.
And then, just like with a 2 by 2 determinant, you're going to have a minus sitting there. So there's a minus. Open up another set of parentheses. You're still positioned right here at this 3. Change directions and start multiplying again. 3 times 5 times 2, that's a positive 30. 5 times 1 times 4, That's a positive 20. What's the last product? 1 times negative 2 times negative 7. That's going to give me positive 14. You have 3 diagonals falling from left to right. That's the first set of parentheses. And then you have 3 diagonals falling from right to left. That's the second set. You could have started here and done 14 plus 20 plus 30. Okay? If it's easier for you to start over here on the far left for the second set of parentheses, you can do that. But you have 3 diagonals falling from left to right minus 3 diagonals falling from right to left. Now let's simplify inside the parentheses. Oh, I'm running out of room. Okay, wait, I can do this. Okay. Working inside the first set of parentheses, we have a negative 175 plus 2, that's a negative 173. A negative 173 minus 24, is that a negative 197? You better check me.
Negative 197. I've already done it in my head.
Oh, okay. So the first set of parentheses is a negative 197. We still have that minus right there. Now let's simplify inside the red set of parentheses. 30 plus 20 is 50, plus 14. 50 plus 14 is 64. Negative 197 minus 64, is that a negative 261? Someone check me there.
Yeah.
Yes? Any questions there?
Now, if you wanted to do this with a calculator like this one,
a TI-83 or a TI-84. And I should have mentioned this to y'all. That little program that we use with those calculators is no longer available from the place that we got it years ago. TI decided they didn't want us having that thing for free. But we have it, and you don't have to have administrative privileges. And so, we can just move it from computer to computer. I have it stored on a flash drive. If you'd wanted that little program, just bring your flash drive and stick it in, and we'll drag it over there to it, and then you can use that TI-83 on your test.
Will it let you do that?
Yes, it lets me do it. That's how I got it over there.
Oh, okay. I assumed that lockdown browser would stop it.
Oh, it might. You're right.
I think it does.
Oh, that's
I don't think you can use it
terrible.
on the test. Okay?
Oh, wow.
That's why the little Calc 84 on your phone, that app works well. But anyway, okay, if you're going to punch this into your calculator like this one, you got to first hit the matrix key, which is in yellow right there. You go second matrix, and you have to enter all these numbers. To do that, you got to go to edit.
You need to tell the calculator what size matrix you're entering.
And which one of these matrices you want to use. I'm just going to use the first one, A. And I say, okay, that's a 3 by 3 matrix. 3 by 3. Okay. Notice it gives me the little matrix, and I just go through entering the numbers. 5, enter. 1, enter. 3, enter. Negative 2, 5, 1, 2, 4, negative 7.
Notice you don't have to recopy the other 2 rows, the columns. You only do that when you're doing it by hand. If you're using the calculator, you enter in the matrix.
And then you've got to enter it all as, make a separate statement. Now quit this. Go second and that yellow quit. Then go back to the matrix, second matrix. You now want to do some math
on that 3 by 3 matrix.
So you go to math, and the very first thing is determinants. Okay? If you kept going down here, you'll see a thing that says RREF, reduced row echelon form. That's how you would take the matrix and write it with ones down the diagonals and zeros elsewhere, okay? But that's not what we're doing. We're looking at determinants. So you say 1, determinant, and then you got to tell it which matrix to use. So once again, second matrix, and either hit a 1 or enter, and better say negative 261 when I hit enter now. There it is.
I think my crisscross method is quicker than all that.
Well, we're going to do the next one using just the calculator to make sure they get the hang of it. Negative 261. As I want to see. Okay. I want y'all to see me do this problem just completely with the calculator. Okay?
Well, if it's all the same to you, I'm going to write it on paper while you're doing that, okay?
And whoever gets done first, the screen's out done.
No, I'm not, okay. I'm not going to. Go ahead, Tony.
Second matrix. I may as well I'm going to reuse matrix A and just put in new numbers. Oh, wait, what am I doing? I didn't say edit. Matrix, move over to edit. And I'm just going to edit matrix A, enter, enter, and now I'm going to just put in the new numbers. 1, enter, 7, enter, 7, enter, 10, enter, 9, enter, 0. Oh, that's probably very annoying listening to me say enter. So I've entered all the matrix. Second, quit. I'll go back to matrix, second matrix. Move over to math, because you're going to find the determinant. And now you got to tell it which matrix to use. Matrix A. 161. If it says wrong, I punched in a wrong number. I forgot I didn't look at the matrix and make sure I didn't punch anything. No. Okay, I didn't mess up. I guess
Y'all want to see that one with my crisscross method?
No.
No? Oh, okay.
I don't want to see it with the crisscross method. Okay.
Someone want to see it by hand? Yes, let's go back to that one and do it by hand. Okay. Let me write it down.
I think the numbers will be a little bit better here because there's a couple of zeros.
Zeros, that's right. When you're finding a determinant, you should be wanting a lot of zeros because it's up here in the matrix. Because if you multiply by 0, the product's going to be 0. Okay, switch over. Let me make sure I didn't miscopy it. So okay. Okay, so we've recopied the first two columns, 1, 10, 3, and 7, 9, 5. We're going to have parentheses minus parentheses. And you start in the upper left-hand corner and start multiplying. 1 times 9 times 0. 1 times 9 times 0 is? 0. 7 times 0 times 3 is? Another 0. 7 times 10 times 5 is 350. Now we go in the opposite direction. 7 times 9 times 3, is that a 189? No, is it a 189? The next one's nice. 1 times 0 times 5, 0. 7 times 10 times 0 is. So we have 350 minus 189. And I sure hope that gives us, what did you get, 161? 350 minus 189. Any questions there?
Oh, okay.
Okay. To solve a system of linear equations, we've seen two methods today, elimination and substitution. There's a third method that uses determinants to solve a system of equations. It's called Cramer's rule. Cramer was a famous mathematician, but
I think he'd roll over in his grave
if he knew that's what Cramer's rule is, what he's remembered for. He's mentioned in every college algebra book in the world for Cramer's rule, although he did so much work involving matrix theory that
this is what he's remembered for.
This is what he's remembered for. Okay.
Okay.
You want to take over?
Okay. So this Cramer's rule is a way of solving this without elimination or substitution.
It uses determinants to solve the system.
So let me write out Cramer's rule. Let capital T, if someone asked you what's Cramer's rule, the answer would be, well, x equals dx over d and y equals dy over d. The natural question is, what the heck are these d's? Let capital D be the determinant, and DET is the standard abbreviation for determinant in any English language math book and on any English language calculator. Let capital let capital D be the determinant of the coefficient matrix.
You're not using the constants on the right-hand side. You're just using the coefficients of the variables for capital D.
So you take the four coefficients, do the little crisscross, and that's capital D. Then let D with a subscript of x, which I'm going to say just dx out of laziness and rather than D subscript x every time. Let D subscript x be the determinant of the matrix formed by replacing the x column with the constant column. And then we'll say define dy similarly. Whatever the subscript is, that's what gets replaced with the constants. Define dy similarly
by replacing the y column with the column of constants.
Okay, let me go.
No, just say similarly.
By replacing the y column with the constants.
And here's what Cramer is remembered for.
Poor man.
Why poor man? His name gets mentioned in every college algebra book in the world. Right. Cramer was able to prove that x will always equal d sub x divided by d, and that y will always equal d sub y divided by d.
X is dx over d, y is dy over d.
You better not mess up on the column of the coefficient matrix. the determinant of the coefficient matrix, because if you do, your values for x and y are all going to be wrong as well.
So let's do an example. What was it?
So let's do it right.
Oh, okay. Oh, that's what I've done for years and years.
Now, look at this problem here. Look at number 13.
Okay, but I just want to write this one down and we'll go back.
We'll go back. Notice, this looks like something you could use elimination with, right? Cramer's rule is just another method to solve linear systems in addition to elimination and substitution.
You start off, write down the four coefficients, and then do the little fast 2x2 crisscross, making the x, just the single x, not all the other x's. Then, we will then replace the x column with the two constants, do the crisscross, that gives you d sub x, then replace the y column, whatever the subscript is, that's the column that you're replacing with the constants. Okay?
It's sort of funny, I was looking and seeing there were problems where use Cramer's rule to find dy, because really there's no time you must use Cramer's rule. You could use elimination and substitution to solve the system, and so there are problems designed to force you to know Cramer's rule, because there are problems where just find dy. I don't think we put any of those on the test, did we?
But Pearson, what they're working towards is
go on.
Okay. So start off.
No, well, we need to finish this. We need to get through with this. You can look at it when at the end of class.
Tim, just go back. Okay.
It's good to say it.
Okay. So write out the four. Ooh, let me move it down.
Is that it? 4,
Uh-huh.
7, 9. Okay.
So you write out the four coefficients. The x coefficient, that's 4, 4, that's the x column. The y column, 4, 2, and do the crisscross. 8 minus 28. 8 minus 28, that's a negative 20. Then you find dx. Whatever the subscript is, that column gets replaced with these constants. So in place of the x column, I'm putting 9, negative 2. The y column stays 7 and 2. And we do the little crisscross again. 9 times 2 would be 18. Then a minus. Now I think we're going to get another negative. We have the minus from the rule, the definition, and then we have a negative 14.
plus 14.
Mm-hmm. So 18 plus 14 is 32. And then one more thing, find dy. Whatever the subscript is, that's the column that gets replaced. So the x column stays 4, 4. And the y column is 9, negative 2. So we have, when we do the crisscross, negative 8, then a minus 36.
So that equals to negative 44.
Negative 44? Tim, can you look and let me make sure I didn't miscopy this problem?
I was thinking for the first one, I was surprised it wasn't giving you.
4x plus 7y is 9. 4x plus 2. Okay.
Okay, that's right.
So if you tried to do this with elimination or substitution, you'd get some messy fractions along the way.
I was just thinking that's one advantage of Cramer's rule is you're going to get these fractional answers without having to manipulate the fractions. If you'd used elimination or substitution, you would have wound up with a fraction and you
adding,
had to plug the
subtracting,
fraction.
multiplying with fractions. Here it's dx 32 over a negative 20. We'll reduce that as a negative. What can I divide
8/5.
these?
Cancel a 4 above and below.
8/5. So there's our x value. Actually, this is a very good example of Cramer's rule.
It is. I was just thinking the same thing.
Because it actually is easier than if you did it with elimination or substitution. The dy, negative 44 over negative 20. That's going to be a positive.
You can
Negative.
multiply 4, so it's 11 over 5.
Uh-huh.
So these two lines intersect at the ordered pair.
Negative 8 over 5, comma, 11 over 5. Any questions over that? This wouldn't be so easy to check with my method of plugging in.
Because of the fractions.
Because of the fractions, you're right. Mm-hmm. So negative, when you've typed in your answer, make sure you put the parentheses around them. Okay.
I have a funny story regarding Cramer's rule. We minored in computer science, and I remember there at one of our last semesters, we were taking this. It was called computer programming for math majors, but Tony and I were the only math majors in the class. It was mostly business programming students that were having to take it, okay, just as an elective. And the teacher goes in on the first day. It's a 4-week summer semester. Teacher goes in and says, oh, well, we're using Pascal, write a program to solve a system of linear equations. Then he shows elimination. It reminds everyone of elimination and substitution. And I remember me and Tony, that's crazy. Just use Cramer's rule. Cramer's rule is number driven. That's all you're doing, multiplying numbers and dividing. There's no variable manipulation. We wrote the program, turned it in. The teacher, who was not a mathematician, he was a business programmer, he was furious. And he went and told all these other people that we had some little trick. We didn't have to use elimination and substitution. And we told them, they're in class. Well, no, it's not a trick. It's called Cramer's rule. And we pulled out a linear algebra book to show it to them. And then this teacher, who was so mad, He said, well, it's not fair. Math majors have an unfair advantage in this course. There was a student reporter taking the class for the student newspaper, plastered the headlines. Math majors have an unfair advantage in a course entitled Programming for Math Majors.
Yeah. I don't think that teacher ever taught the course again.
He never taught it again.
But there's still one more of these Cramer's rule problems. Let's do it and call it quits for the day. But,
Yes, we did keep that newspaper.
Yeah.
It's somewhere stored away, or else we scanned it. But we did keep it.
Yeah, we
all the math faculty there were just so proud of us for standing our ground with Cramer's rule. And oh goodness, I remember.
I just did Cramer's rule because it's so easy. If you're going to write a program, a computer program, it's so much easier to do this. It'll multiply those numbers and stuff than try to eliminate and substitute. Oh, well. But anyway, this problem here, number 14, is actually tailor-made.
For what method? Don't tell them. What method? If you weren't going to use Cramer's rule, I'll give you a hint. It's either elimination or substitution. I would say it's tailor-made for elimination.
Okay, let me do. Okay.
Too bad.
Okay. Oh,
you're just working it on.
yeah. Well, I've written it down, and now I'm going to find D. Write down the 4 coefficients.
Oh, that page is so busy, Tony. I'm drawing a green line here so y'all can tell where number 13 stops and 14 begins.
Then we do our little crisscross. -6 minus 15. So that's a -21.
Then you would do the x, which is -3, then -1, 3, then 8.
No, I don't think so.
You replace the x with these constants.
Oh, okay.
So the x column is -1, 8,
5 and 2.
and the y's 5 and 2.
The subscript tells you which column you're replacing.
So it would be -2
2
minus 40, which equals to -42.
Okay. Minus 40,
Equals to -42.
That's a -42.
Which we can already determine based off of the previous answer that it would just be 2.
Yeah. X would be -42 over -21.
So parentheses 2, comma.
Well,
Go ahead and find.
I'm going
this
to do
one.
y and then. So,
-3 and 3.
yep. Leave the x's alone. -3 and 3.
That would be -1 and 8.
Replace the y with -1 and 8.
So the first number would be -24. And it would be plus 3 because it would be a -3.
Oh, did y'all hear that? Perfect. -24 minus
Minus
a -3.
2 plus 3, so it would equal to -21. Divide that by -21, so it's just 1. So it would be parentheses 2, comma 1 parentheses.
Okay, did y'all hear all of that? So, did y'all follow my adding and subtracting and multiplying to get these numbers here? So, x is dx over d, -42 over -21,
So it would be 2.
2.
Then for the y, it would be d subscript y over d, which is -21 over -21, so it is equal to 1.
Oh, do I have room to write my ordered pair?
Yes, you do.
X, Y. Okay?
Number 14 could have been handled pretty nicely with elimination.
Oh, yeah, would have worked out, I think,
But
nicer with elimination.
But number
13, where you have those fractions, give that a try with elimination, and you're going to wind up.
Okay, I'm just punching in the answer, and then I'll go back.
That's the last one we're doing for today.
And we'll pick up here on Tuesday.
Maybe